is up, my dudes? And here we are, Chapter 3 of the CCNA 1 class. So, this is what we're going to be talking about today, blah, 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 blah. This is kind of a dry chapter, not a whole lot of technical, hands-on kind of stuff, but it's a lot of foundational concepts that you really need to understand. So, let's start off with the rules of communication. You know, when we talk about communication, there has to be a source and a destination, or a sender and a receiver, and there has to be some kind of channel or media. So in networking, when we talk about media, we're talking about the cabling that we're using, or the transmission method. So if two people are having a conversation and one speaks English and one speaks French, obviously that's not going to work because the media or the channel is different. Just like in networking, if one node is sending radio signals and the other node is sending electrical impulses, that's not going to work. So we use protocols, and they're just like rules for effective communication. It identifies, it has ways, it's the rules of how to identify the sender and the receiver, the common language and how what kind of grammar we're going to use, or when we're going to stop sentences, things like that. The speed, how fast I can talk, things like that. So this stuff is all kind of common sense. So when they talk about message encoding, what we're saying is, let's say you have a Word document and you want to send it to the server, or you want to pull it from the server, something like that. That Word document gets broken down into a whole bunch of tiny pieces, and each piece needs addressing information. It needs a port number, it needs an IP address, it needs a MAC address, things like that. So that's really the encoding process. So basically we kind of go through the list, we add a bunch of information on the little packets, and then we start sending them out. So you might wonder, why do I need all this addressing, if something's going to be sent just inside my local network? Why do I need all this different stuff? Well, it's kind of like the same rules that we have for sending a letter. When your local postal carrier goes to the office and picks up his mail for his route, he doesn't really look at what state is listed or even what city or area code. Because he's just interested in the street number and the street name because he needs to know where to drop the mail off. It's like that too. Your firewalls will typically look at port numbers because we block things by port number. Hey, let's block FTP and things like that. And then routers look at IP addresses, and switches look at MAC addresses. So the packet never really knows what devices it's going to encounter on its path. So because of that, we have to have all that addressing information on each individual piece. And the process of adding that information is called encapsulation. So I like to think of it as little semi-trucks. You've got all your data, which is the bed of the truck, and then you've got the engine, which is really all your header information. The IP address, the port number, the MAC address, and they're all driving down the Ethernet cable going to their destination. And then different protocols have rules for how those semi-trucks or that stuff is going to work. Like you can see here, this is just a kind of a representation, but there's always something to signal the start of the frame or the packet. Typically we call that a preamble. And then there's usually some kind of error checking at the end of the frame, a frame check sequence or something, so that we can make sure that it wasn't damaged in transit. And just like when we navigate, land, we always need a source and destination. When you go to MapQuest and you're going somewhere, it always asks you for two pieces of information, the source and the destination. Where am I going from? Where am I going to? Same thing with these packets. And when you think about it, it's actually pretty amazing. When we take a Word document, break it up into 10,000 small little packets, and then address all of those packets and send them, and the stuff occurs so fast. All right, and then there's message size. Obviously we need to break long message up into smaller parts or sentences or paragraphs, things like that. So long messages must also be broken down. So each piece is broken down into a separate frame, and each frame has its own addressing. So when we're sending those pieces out on the line, we send frames, and each frame has its own addressing. And just like a letter from the post office, it has all the addressing, even if it's not required. So if you and I are in the same room and we're just connected to a switch and we're sending stuff back and forth, we don't necessarily need port numbers and things like that. But just because of the rules, all that stuff is included. Just like if you were to send a thank you card to your neighbor, you would still have to put the city, state, and zip code. All right, other rules might be the timing. who gets to talk first. If I'm dealing with walkie-talkies, whoever holds their button in gets to talk, and the other guy just has to listen and can't talk. But if we're talking with a phone, we can both talk at the same time. So there has to be some method. What happens when two people are talking at the same time? Or in networking terms, that we call that a collision. So packets are coming in and out at the same time, so they collide. And then we also need some kind of method for flow control. What happens when the buffer gets full because you're sending too much information, I can't process it fast enough. So there has to be methods of timing, what to do when we have a collision, what to do when stuff gets overwhelmed, or flow control, and what to do when nobody's listening, or when my response times out. And that's where we have the uncomfortable pause, like when your wife tells you, "Did you do that?" and you're like, "Duh," and you're doing the deer in the headlights thing. So all these rules get combined into a package, and we call that a protocol. And there are a bunch of different protocols that we use on the internet, or just in PCs in general. All right, then last, the delivery options. A unicast is a one-to-one delivery. So my PC to your PC, or my PC to the file server, things like that. A multicast is one-to-many, but not all. So when we have a net meeting, a bunch of people will all connect to the net meeting. That's an example of multicast. A broadcast is one to all. So when your PC first starts up at a business, it doesn't have an IP address typically. So he has to send a broadcast out to everybody on that network and say, "Hey, I need an IP address." And then the DHCP server would get that broadcast, and then he would respond to it and give him an IP address. So that's an example. So unicast, one-to-one, multicast, one-to-many, and broadcast, one-to-all. All right, so let's talk about some of the specific protocols and stuff. So long ago, when dinosaurs roamed the earth, different vendors created different things, and things didn't really work together that well. If you bought let's say an IBM router, you typically had to have some other IBM stuff to go along with it, otherwise it wouldn't work. And that was one of the, I guess, things that really kind of prevented the adoption of PCs and stuff like that, and computerized offices. And then luckily, the standards people kind of got together and they said, "Hey, we need to create some standards for these things." So they came up with a model called the OSI model, Open Systems Interconnect model. And then the model had 7 different layers, and different protocols worked at different layers to do things. And as long as you could build your hardware to work with this model, then everything would be interconnected or interchangeable. And that's why we can have Dell PCs, and we can have HP ProCurve switches, and we can have Cisco routers, and IBM servers, and everything else still all works together. So in this model, we have different layers, and each layer typically has its own kind of protocols at that layer. So networking protocols are examples would be like HTTP, TCP, and then IP, UDP, AppleTalk. If I'm dealing with web browsers typically, use the HTTP protocol to open and close websites. But if I'm just sending information back and forth between PCs, I'll probably be using TCP/IP. So different protocols for different jobs. So like I said, different protocols for different jobs. So HTTP would be at the top layer of the OSI model, and that's something that the programmers would actually code into their product to make the web server and the web clients interact together. Now TCP is a networking protocol, and this manages individual conversations. What happens when you open 2 different web browsers? You open one for gardening and one for monkeys throwing poop. How does the PC know when stuff comes in, which web browser to put stuff in? I don't want gardening and monkey poop, mixed together. So the TCP protocol handles those individual conversations. And then you have IP, how does my stuff get to where it needs to go? So now we're talking about addressing and making sure things get delivered to the host. And then we have Ethernet, which is a communication method that we send stuff on cables. So Ethernet uses copper cables and sends things as pulses of electricity, where your wireless would send radio signals, across the air, and fiber would send things, as pulses of light. And we'll talk more about these protocols in depth as the course kind of moves along. All right, so these aren't all the layers of the OSI model, but they're some of the main layers. So we don't really deal with the application layer, because this is what software designers and programmers kind of work with. So there's a bunch of different protocols at those levels, HTTP, DNS, which is domain name service, DHCP hands out IP addresses, and FTP, how do I transfer files back and forth. There's OSI protocols. There's Apple Talk, which was miserable, and then there was Novell. And years ago, Novell was like the big one. It was kind of odd that Novell kind of lost that networking thing. They were the giant. Then at the transport layer, we have TCP or UDP. TCP is a connection-oriented protocol. So if I'm doing if I'm going to like a web browser, or I'm transferring files, or I'm opening up my email, I can use TCP to make sure the connection's there, and to check to make sure all the packets get to where they need to be, and if any are damaged, it'll ask it to resend, things like that. But UDP is a connection list oriented. It just kind of sends it. It's like a postcard. I send it to you. I have no idea whether you got it or not. And TCP is like a phone call. When you answer hello, then I know you got the phone. I know you heard me. And if you don't understand something that I say, you'll say, hey, can you say that again? So TCP, connection oriented, like a phone call. UDP is like a postcard. I send it. I have no idea whether you got it or not. But UDP is great for video and voice, when I need to get the packets there as fast as possible. All right, if any of you guys ever played the original Diablo game, that had networking built in, but it did not use TCP IP. It actually uses IPX SPX. So if you were running a small network in your house, you had to run NWLink, which was Microsoft's version of IPX SPX. And then you could network and you could all play together in Diablo. But Novell kind of went the way of the dinosaur, and now they're dead. And that's why almost everything now is TCP IP. All right, so the internet started, way back in I want to say the 60s, 70s, things like that. And it was funded by the Department of Defense, and it was just to keep a line of communication open in case the Russians nuked us in America. And luckily that didn't happen. And then some research organizations got in there, and some universities, and it kind of spread from there. And back then, that's when they developed IP version 4. Now, back then, they had no idea how big PCs were going to be, 20, 30 years down the road. And IP version 4 only supports, I want to say, 17 or 18 million addresses, something pretty small. So in today's world, obviously, there's way more than 17 million, PCs and stuff out there. So they had to come up with something else. So that's when they came up with IP version 6. So IP version 6 is relatively new. The first IPv6 day when many websites and stuff went kind of activated it was June 8th, 2011. And with IP version 6, each person on the planet could have 100 addresses, and each address could give you 10,000 networks, and they would still not run out of addresses. So that's how big IPv6 is. So eventually we'll start talking about IP version 4 and IP version 6, and we'll do some subnetting, things like that. All right, moving on. All right, when you look at this, it might be confusing because you're like, well, if TCP is here and HTTP is here, aren't they separate? They kind of are separate. So HTTP is built into websites and web browsers. But TCP establishes the connections between those two, and then the HTTP kind of kicks in. So a lot of these protocols work very well together, and sometimes seamlessly. So I'm going to talk about these individually. DNS is domain name service, and that's what keeps track of friendly names to IP addresses. When you go to google.com, the friendly name obviously is google.com, and that way we can remember that. If we had to remember all the IP addresses of different websites, you'd probably only go to 3 different websites. So that's what DNS is. DNS tracks the friendly name to the IP address. And that's why you can either use the friendly name or IP address, like in ping or whatever you want to do, because there's a DNS server somewhere that kind of translates that for you. All right, and then to hand out IP addresses, years ago it was BootP was the protocol, and nowadays it's DHCP, which is Dynamic Host Control Protocol. And that hands out IP addresses to users. So typically at home, your PC doesn't have an IP address. When he first starts up, he asks for an IP address, and then your home router kind of hands him an IP address. All right, then we have email, simple mail transport protocol or post office protocol, then a newer version of IMAP. And then when we're sending files back and forth, it's file transfer protocol or trivial file transfer protocol. And we're viewing things on the web, we're using HTTP. And then at the transport layer, we have UDP and TCP. And this decides how I'm going to get there and back. Am I going to establish a connection, or am I not going to establish a connection? TCP makes a connection, makes sure everything gets there in order, and if anything that gets damaged gets resent. UDP doesn't care, just sends it out as fast as it can, hopes it gets there fast enough. And then IP and NAT are used, as far as addressing goes. ICMP is used for messaging across the internet or for troubleshooting. When we send a ping packet, that's ICMP. Then we have routing protocols that we'll talk about eventually in the Phase 2 class or Phase 3. And then you have all the lower level like ARP. ARP is Address Resolution Protocol, and that's IP address to MAC address. And then there's PPP, which is a layer 2 encapsulation method. Then we have Ethernet, which is our cabling. Then we have different interface drivers. So a lot of different things at different layers. So don't get too hung up on this stuff now. We're just going to talk about the OSI model. As long as you get that, you're good. Ooh, don't know what happened there. So here they give you an example. The web server prepares the HTTP page, and then the transport layer breaks the data into segments and identifies each. So when you go to a web server and you view the page, you're not really like kind of viewing the page on the web server. What it's doing is it takes a copy of that page and it breaks it down into smaller pieces. Then it uses another protocol, either TCP or UDP, to send it to your PC, and then it gets rebuilt, and that's what you're viewing. All right, this slide here is a good place to introduce the actual OSI model, because they don't do it for a few slides down. So let's talk about that. All right, this is my favorite picture of the OSI model because it shows all 7 layers and a lot of different stuff. Don't worry about this gateway and things like that. So the OSI model, at the top 3, you have the application, presentation, session. Now these 3 layers are typically software based. These are things that programmers and coders worry about. As far as Cisco goes, we worry about the bottom 4 layer, the transport, network, data link, and physical. So whenever let's say you create a Word document, you're going to program in how it's going to allow any built-in compression or things like that, how it's going to share stuff between different versions of itself. And that would all be coded at the software layer. And at any time in these 3 layers, we typically call data at these 3 layers. We just call it data, or we call it PDUs, protocol data units, or packet data units, whatever you want to call it. And then once it hits the transport layer, at this point we actually add a port number. So we add a port number to allow for flow control and session management. And that's pretty big, because in that way when you open up 2 different web browsers, your stuff doesn't get mixed up, so we can keep the sessions separate. And that happens at the transport layer. And then we go down to the network layer, and here's where we actually do the IP addressing, where your PC actually gets its address so we can communicate with everybody else on the internet. And then we come down here to the data link, and this is where we activate the MAC address. And a MAC address is a address that's kind of burned into your NIC card, so that and then it kind of identifies the maker of the NIC card, and then like the serial number of the NIC card, and that way things kind of can be traced that way. Microsoft tends to refer to that as a physical address because it's physically burned into the NIC card somewhere. And then we have the physical layer, and this is where we talk about how things get transmitted. Am I going to use a pulse of electricity in a NIC card? Am I going to use a wireless card and use radio waves to send stuff through the air? Or am I going to use a fiber card and send things through as pulses of light? Now there's a couple ways to remember these different layers, and it's usually from top to bottom it's all people seem to need data processing, and then from the bottom to the top, please do not throw sausage pizza away. So whichever way you want to remember that, all people seem to need data processing, please do not throw sausage pizza away. So either way. But as we add this addressing information as it comes down here, we call it different things. So at the top 3 layers, we just call it data or PDUs. Then when we hit the transport layer and we add a port number, we call it a segment. And then when we get to the network layer and we add an IP address, we call it a packet. Then we get to the data link layer and we add the MAC address information, then we call it a frame. And then we send those frames, the physical layer actually converts those frames into 1s and 0s, pulses of electricity, pulses of light, or radio waves, and that sends them down. And then different hardware acts at different layers. So a hub or your NIC card work at the physical layer. A switch or a wireless access point work at the data link layer. Routers work at layer 3. And at layer 4, let's say firewalls, because firewalls deal very heavily in port numbers. So we'll just say a firewall, even though you can still block things by IP address. So we'll just do it that way. So this is the OSI model, and as long as you build your switches according to the OSI model at layer 2, and they follow those protocols, then your switch will work with every other switch out there. All right, there's also this one kind of shows you, like obviously here it's called data, then segment, packet, frame. I always remember it as like SPF because I'm going to the beach, and then everything's always bits. Everything is always broken down into the smallest pieces, and then we send 1s and 0s. So, and then in short, so remember, we're only worried about the bottom 4 layers. So the transport layer is end-to-end connectivity. How am I going to connect to you? Is it going to be a connection-oriented protocol or connectionless? Am I going to make a phone call or send a postcard? And then here we worry about how am I going to get there? What's the path to get from me to you? Things like that. And then here we have the physical addressing. The MAC address gets applied, and we start focusing on that. And then that's where we have ARP. All right, so those can be found again on Google Images. Just do OSI model and you'll find that stuff. So as we move through the OSI model and we go down and we send the packets out, when they get to the receiver kind of brings those up through the OSI model and starts stripping that information away to get to the data. And that process of adding and removing the different headers on there is encapsulation as I move down the OSI model. And when I get to the receiver and I'm moving up, we call it unencapsulation as we're kind of coming out the other side. Or maybe decapsulation, whatever you want to say it. All right, so there are a ton of these open standard organizations. We're not going to talk about these too much in depth. You can kind of look at these on your own. So where's IEEE? That wants to be on the next slide. So there are obviously the Internet Assigned Numbers Authority, assigns IP addresses. And my understanding is currently they don't own any more IPv4 addresses. The service providers have purchased all of those. And then so the IEEE is the one that kind of like works on the wiring standards and things like that, especially networking. So a lot of your stuff will be is IEEE certified, things like that. All right, so enough about protocol. You can read those as you want. There's a thing about researching standard organizations. And then they finally start talking about the OSI model. So again, 7 layers. Now the Department of Defense model only has 4 layers. They call this the TCP/IP model. Sometimes they call this the Department of Defense model. And for some reason that shows up on your CCNA exam. And honestly, this model makes more sense because we're not worried about the top 3 layers because those are all application layers. A program, when you design the application, those are things you need to think about. And then these 2 are separate. And then this one, when we talk about physical addresses and then sending things out, that all happens on your NIC card. So it's kind of makes sense to group those 2 together. And again, the whole benefit is that to make things all work together, so you're not tied into one specific vendor like you were in the early days. A long time ago, if you did Novell networking, you were stuck with all Novell products, and it was miserable. So maybe that's why they died. All right, so again, they talk about, make sure you understand like what each layer does, because you will see that again sooner or later. And I think I've discussed that enough. All right, so again, the TCP/IP model, again, early 70s, just a little bit different model, but again, still an open standard. There's the 2 together. Oh, they're so pretty. So the CCNA and actually the Net Plus both focus on the OSI model because that's the big one. All right, hey, there's a packet tracer this week, but it's very weak. Basically, there is no score. You just kind of like walk through and it tells you exactly what to do, and then you just observe some traffic. I won't be going over that in a lab video this week. All right, data transfer in the network. All right, so large streams of data, like let's say you're doing a video conference, obviously they're divided and broken up into smaller, more manageable pieces. When I send a Word document, I don't send the entire Word document. I break that Word document up into 10,000 smaller pieces. I send those smaller pieces. And because all these different pieces are on there, we can send different pieces from different things. And they call this multiplexing, which I don't necessarily know if that's a good way to describe that. That's more like a converged network. Early, and we're just talking about maybe 15, 20 years ago, people had a different network for everything. At the hospital system where I worked, they had a coax cable network for video conferencing and for all the MRI cameras and the radiology system. And then they had a data network for their data computers, and then they had a phone network for their phone system. So there were 3 different sets of wires all up in the ceiling. But nowadays, all that stuff runs on the same cables, and we call that a converged network. Multiplexing, in my view, is when you tie multiple streams together. As an example, again, we're going back 20, 30 years now. It was very expensive to buy, let's say you have a main office and then you bought a new main office 6 miles down the road. And you wanted to connect that office to all the stuff that you had at your main office, like file servers, email, internet. You really had 2 options. You could either buy phone lines and connect it that way, which again, obviously that was pretty popular back in the day. Or you could buy a T1, and a T1 was a 1.5 megabit copper line that you bought through your provider's network. And they were very expensive, hundreds of dollars a month, and you had to sign like 5-year contracts on these. And sometimes, depending on what provider you went through, like they would go up and down quite frequently. So instead of buying the T1, what we would do is we would buy 4 or 6 phone lines, and we would plug them all into a device called a multiplexer, and then that would connect to our main office, and our main office would also have a multiplexer and use those phone lines. And then we would just use those phone lines to kind of like band it all together and send me multiple traffics together as one stream. So that was really what multiplexing was. So again, each piece has to be labeled. If part of the message fails, it'll need to be retransmitted, so sometimes that can cause issues. Now here they say that a PDU is what data is at each layer, but that doesn't really make sense, because why do they call it a segment, a packet, and a frame? So it's a packet network layer PDU. I don't know. I've always remembered it at the top 3 layers. It's always called a PDU. Then it's segment, packet, frame. Then it's obviously at the lowest layer we call it a bits. You'll never hear anybody talk about, hey, let's talk about those network layer PDUs. That doesn't happen. We talk about packets and frames and segments. All right, so don't forget, encapsulation is working our way down from the top to the bottom through the OSI model and adding addressing information. Decapsulation is when I'm working the other way from the bottom to the top, and I'm removing that stuff so I can actually use the data. All right, all devices on the network that are going to work on the network need an IP address, and you have to have anytime you're sending stuff between somewhere, you need a source and destination. Just like if you go to MapQuest, they need to know where you're starting from and where you're going. So as you're going through that OSI model and they're adding addressing information, they're always adding a source and destination address. There's a source and destination port number, a source destination IP address, and a source destination MAC address. So there's a lot of addressing that kind of goes on that stuff. And then the data link layer really is, here's how I'm going to format the packets, and here's how I'm going to send them, here's how fast I'm going to send them, and here's how I'm going to encode them. So if I send from my NIC card to your NIC card, I'm going to send pulse of electricity, and you'll get those as 1s and 0s, and then you'll know how to rebuild it. If I'm sending fiber, then you'll need fiber on your end, and we'll send stuff, and you'll need to know how to rebuild it. So that's where the data link layer kind of comes into play. How am I going to format these frames, and how fast am I going to send them? What speed? How big can they be? Things like that. All right, if you're traveling on the same network, like at my college, every classroom typically has like between 24 and 30 seats, and they're all plugged into the same switch. So each classroom has a dedicated 48-port switch, and all PCs in that classroom are plugged in the same switch. So whenever I communicate with somebody in the classroom and I send them something like a file or whatever, we only go through the switch. So it goes from me to the switch to the next guy, that kind of stuff. I only use routers when I need to connect to a different network. If I need to print to another classroom, or I need to access the content management system that's in the server room, then I'll hit a router, and then that router will route me to the proper destination. So that's what routers do. Routers connect networks together. Switches kind of keep everybody in the same network together. And switches will use a MAC address, which is a 12-digit hexadecimal address, where a router uses the IP address, which is 4 different binary octets. And we'll talk about all that, so don't worry about that part right now. Eventually you'll have like 2 or 3 chapters where we'll just focus on the numbers. So again, I use a router. If I have to go to any kind of remote device, something that's not attached to my switch, I typically have to go to a router, and then I have to get routed to that network because those networks are kept separate. And that way we can keep security, or we can restrict access and do different things. But what's important here is to know, whenever you send, like let's say my PC sends something to this guy, everything goes through the OSI model, and I do the encapsulation process. All my packets go here, and then theoretically they would go to here. And then he would decapsulate them, and he would remove that stuff. But it's different when I go to a different network. When I send something, let's say, to this server, what happens is all my packets it gets all encapsulated and hits the switch, and the switch sends it to the router. The very first thing the router does, it removes the layer 2 information, the MAC address, because the MAC address information on a frame is always local to the network where it's at. So when I send from here to here, it gets removed, and then it gets new information put on for this piece right here. And then when that hits this router removes that stuff and puts new information for this local network right here. And then when this router gets it, he removes the layer 2 information and puts new layer 2 information here. So this web server, every time he receives something, the source MAC address is always going to be this router. And because of that, you can't really track things using the MAC address. You can only track things with a MAC address on the local network, because routers remove that MAC address information and replace it. And again, we'll talk about that again eventually. All right, so to sum it up, there's Wireshark is kind of a neat tool that allows you to actually see the different packets that are hitting your PC. I highly recommend it. I even recommend getting maybe a book or a Udemy video on how to use Wireshark, because it's really cool. This is another lab. I have no idea where this lab is because it's not in my file. And then make sure how do you facilitate communication? Well, we use protocols to facilitate communication, and different protocols have different rules. And different protocols have different specializations, like HTTP is for web stuff, so that would be the role of HTTP. And then we've kind of talked about how devices work on a LAN. Switches interconnect everybody in the same LAN, and then if I'm going from my LAN to another LAN, I need to go hit a router and kind of go through there. All right, and then we have, yay, Cisco. And then make sure you understand all these different things. And that one, bam, that's a lot. So make sure you're familiar with the OSI model. Make sure you know what data is called, because you'll see a question, at layer 2, data is called a frame. Stuff like that. And again, we'll talk about these protocols again 3 or 4 different times in all the Cisco classes, so don't worry too much about memorizing exactly what each one does. But there are a lot of acronyms in networking. All right, this is the big one. Make sure you know what these are, these different things, or what their definitions are. And with that, so remember, there's no lab video this week. That's kind of it. So have a great week, folks.